This is a proposed pre-collimation procedure recommended to the TMT team by an amateur astronomer. It is not an official TMT study. In 2004, I developed a virtual pinhole laser collimation test for Cassegranian primary mirrors, and in this presentation I am adopting the methodology for multiple mirror adaptive optics arrays, as for example the 30-meter telescope planned for Mauna Kea in Hawaii. The virtual pinhole test shown on YouTube is summarized here, highlighting its key elements. What the test demonstrates is that a laser beam can be mounted and aimed to define an optical axis for a primary mirror, and that mirror can then be aligned to fall exactly on that axis. This is done by illuminating that laser so as to strike a 3M-like retroreflecting film near the primary's center of curvature, effectively creating a new light source, a virtual pinhole. The physics of the reflective film will be that most of the beam energy will be reflected back, but slightly scattered within a cone of only a few degrees. Enough of that light will pass around the secondary mirror to reach the primary, this time reflected back as an optical image, now a ring from passing around the secondary, and also placing it on the screen near the virtual pinhole. The collimation itself is performed by adjusting the primary mirror screws until both the virtual and the ring images become coincident. The key message is that the primary mirror can be made to be coincident to the pre-aligned target laser beam. In a multi-mirror array application, everything will be similar, except observe that far more light energy will be present to assure bright images in high contrast. A separate laser beam will be dedicated for each mirror segment, as each mirror has its own unique optical axis by design. Life cycle costs will justify this. A camera will record the screen images for pre-collimation analysis to make corrections to the mirror segment relative to the beam and adjacent sets of segments for possible beam corrections. The objective will be to pre-adjust mirror segments to be close enough after daylight adjustments for adaptive optics to take over for final and atmospheric corrections. Presently, a small portion of prime observing time is allocated for this pre-adjustment. A simplified graphic demonstrates the key elements in the adaptation. 3 zones of hex mirror arrays are shown: a red outer zone, a blue inner zone, and a green mid-zone. The purpose is to demonstrate that in array optical systems, radially outward zones, small r, do not have the same radius of curvature, large R, as inner zones, but are progressively longer. This is in order to bring all the rays coming from infinity and falling on the mirror to come together at F1. The inner blue zones must come together first, then the mid-green zones and the last red zones, as shown in this detail, where the centers of curvature R1, R2, and R3 sequentially come together. The axial scale has been exaggerated to separate the rays, but generally, while the zones remain relatively coherent, there will be a tendency for separation between the zones. Of course, none of this is visible to the eye unless a reflective screen is selectively positioned to reveal section views. In this case, these 3 patterns would be found at the centers of curvature of the blue, green, and red zones. Note that an image at the red zone R3 will find diverging blue and green zones where red zones are still converging. As the blue zone converged sooner than the green zone, the scales and magnifications are different, causing separations and other distressing effects for analysis. Returning now to the overview, because each mirror segment has its own optical axis, taking for example a mirror segment at A, where a target laser is placed, it will be an objective to align that beam and all of the others similarly to converge on the optical axis at B to impart the proper correction for optical aberrations. Rays from all mirror segments of or near that zone will be coming together at this same point, making it difficult to control or manage first-order collimation of these mirrors. It may be better to allow all such beams to continue through point B on the array axis and proceed to a secondary target at B prime, some arbitrary distance behind, offering comfortable separation for easy management of all the first-order collimations. As a final observation, note the complete path of the mirror segment wavefront, diminishing in size as it converges to a point image at B, and then it expands as it diverges to B prime. This slide shows how distortion between zones may be reduced by having smaller, higher resolution segments with smaller differences in radii changes. The key point in this slide is that placement of the reflective screen inside of the first center of curvature is the best position for image analysis. The distance inside the first center of curvature should be determined to achieve a workable image size for the smallest zone metrics. The factor at the other end will be the diameter of the outer zone to be reasonable for sizing a screen outside of or mounted to the dome structure for ease of use. As the final objective is to align mirror segments to target lasers, there is a risk of creating confusing extra images by adjacent mirrors. The figure to the right suggests spreading out pattern sets for illumination of the 6 repeat groups and sequencing them until all segments have been covered. An option center figure would have a distinguishable array centerline axis to establish a standard datum reference for center and or radial coordinates. A factor demonstrated in the lower left, callouts A through D are distinguishing flaw properties visible by overlapping or separation of mirror segment wavefronts. These are the 3 variations of usage. The first is the baseline TMT operation, where some near prime time observation time is allocated for pre-setup of mirror segments following routine housekeeping and maintenance tasks. These are already allocated by planning. Mode A is a procedure where an arc bridge can be elevated in daytime to capture images for pre-collimation, bringing them within adaptive optics accommodation range. This could reduce prime time observation allocations for pre-collimation. Mode B is a variation where first-order corrections may be made concurrent with observing time data collection. A benefit here may be a change in a specification allowing lower-cost hardware and or smaller but faster response times to adaptive optics systems. This view shows the aforementioned arc bridge that could be adapted to position the Mode B screen. Note that all tolerances are loose and are not critical, since analysis would be based on computer-corrected imagery. Note also an optional retractable test tower may be employed to tighten collimation tolerances if that is needed. And this would be for Mode B type application for concurrent corrections of structural flexure and atmospheric adaptive optics corrections. The shaped arches are for the purpose of eliminating extra diffraction patterns, as the decoupled dome would introduce unique patterns. Arrow issues may be a problem with this. Dedicated laser target markers for the mirror segments will require their placement on the optical axis and aimed from the same foundation structure that supports the mirror for close coupled stability. They'll be aimed at Hartmann-like targets beyond the centers of curvature. Passage of the beam through the mirror maybe through a core hole in the blank at A, or an inserted optical window as shown in B, or in a variation where a window is bonded into the blank before grinding and polishing have been completed as at C. In the course of this investigation, a simple single laser concept shown here became a new candidate. Utilizing the virtual pinhole created by a laser strike, an on-axis laser beam striking a bead reflector screen could illuminate the entire array from one source. There would be no critical tolerances for placement of beam and screen other than being inside of R1 center of curvature. Note that this does not have the accuracy of a dedicated target lasers to which the mirror segments are aligned. With a screen perhaps tailored like a movie theater to better distribute the light, that would provide a large single image of converging wavefronts, illuminating and presenting all mirror segments, now with eye sensitivity and visual magnification of misaligned edges. All flaws would stand out. Some interesting factors are the zone arrays are consistent within themselves. That is, as the zones expand relative to their sizes and hexes maintain their near contact relationships to each other. In or out of focus is not an issue for assessing where the edges actually are. Edge patterns are the edges of wave fronts and are always sharp, like sunlight edges, through a window. Misalignments between hexes are magnified in that overlaps of wavefronts double up in an intensity. Gaps, likewise, are subject to the eye sensitivity to detect variations in gap size or parallelism. Three misalignment flaws are shown at the arrows. Looking at it here at a TMT scale helps minimize the distortions, but there would be more than are shown here in this PowerPoint graphic. The key factor to be aware of is that with a single laser source and perfectly nested hex wavefronts, even minor misalignments stand out in bold relief as shown at the arrows, both by doubled intensity overlaps and black zone gaps. Two obvious misalignments reveal themselves here. Because the error flaws are caused by gaps in or by a doubling up of the wavefronts from optical surface discontinuities, the placement of the illuminating source is not critical, it's just a broad light source. Therefore, the reflective bead screen film can be replaced by a simple convex mirror. In effect, instead of scattering diffused light emanating from a bright spot on the screen, the laser source will appear to be a virtual point source of light from behind in the mirror, illuminating the entire primary area with a cone of light. This has advantages in that it both presents a more uniform illumination for the images presented, and because the virtual image does not really exist, the screen can be brought even closer to the array, requiring less protrusion of screens and supporting structures through the open dome. I have added some of my background information to conclude this presentation.